This is a lesson on Doppler effect for light in university physics. I'm going to hop right into it. I've covered Doppler effect for sound waves in a previous lesson. And that was a much more complicated equation. There was a plus and minus going on the top and bottom, the way that I taught it with a absolute relative frame velocity rather than a relative velocity. When we look at Doppler effect for light, we're going to look at the relative velocity between the two objects that are passing the light between them. All right. So Doppler light shifts. In the Doppler effect, light shifts in frequency and wavelength of the observed wavelength when the observer and source are moved towards or away from each other. All right, so this is a general equation. What I'm going to note here is that V is the relative speed between the source and the observer. So a lot of times when we're measuring light, it could be on the surface of the earth, but a lot of times we're looking at out in space. Okay, so there's no absolute reference frame out in space. We just know the velocity between the two objects. Either they're moving towards each other or away from each other. So that's what we're looking at here is V is defined as that relative speed. You could put a relative down on the bottom in that subscript there to remind you that is what you're looking at. It's pretty clear in problems when you read it, though. Due to the relative speeds, signs are always opposite one another. So when you use this equation, you will use it with the plus on the top and the minus on the bottom, which is why I have these symbols in here the way they are. So plus on top, minus on the bottom. Or let me choose a different color in here. Minus, if you use a minus on the top, you're going to use a plus on the bottom. And the difference is if you're moving towards or away. And so we already know about Doppler shift. We know that when two objects are moving towards each other, for whatever reason, they're moving towards each other. And it could be they're both moving in the same direction, but one's moving faster than the other. When the relative velocity between them are towards each other, then what we're going to see is that the frequency, we're going to have a shift in frequency, right? The frequency will go up, an increase in frequency. Those waves are going to be received quicker, which means, and we know this, the speed of light is given by lambda f. Right? So if the frequency goes up, that means that the wavelength has to go down. Okay? And so if we want a wavelength to go down, lambda, the original S stands for source, O stands for absorbed, source and absorbed. We want the observed to be less than the source. We want this to go down, which means that we need this to be a factor that makes that's less than 1, I would say, right? The only way that's going to happen is if you have a minus in the top and a plus in the bottom, okay? And so when they're moving away from one another, I'll just go like that, V relative, when they're moving away from one another, the frequency is going to go down, which means that the wavelength has to get longer. It'll get longer in that situation. And so if we want a longer wavelength, if we want the observed to be longer than the original, then we'd have to multiply by something larger, and that's why we're going to put a plus in the top and a minus in the bottom. Okay, so hopefully you followed that. I have a picture here. I think a picture is worth, what they say, 1,000 words or something like that. When I look at a picture here, and I grabbed this from some random place, I don't know where, and hopefully I don't get pulled for copyright or something, but I like the picture. This is a rotating star, and like I said, out in space, we have things we're looking at that's sending light to us, to Earth, right? Not directly to us, in all directions, and we receive it at Earth. If it's not rotating, then all of the light coming from that object is not going to be shifted at all. But what we're looking at, and you may be familiar with these terms of redshift and blueshift, how we get redshift and blueshift, and what that says about if an object's moving towards us or away from us. So when we're looking at a rotating star, it's big enough for us and rotating fast enough for us to notice that there's a side that's moving towards us, right? Toward. And there's a side that's moving away from us. And like I said on the previous slide, the shifts are going to happen for each one of those slides. So if it's moving towards us, the frequency is going to increase frequency. And notice in this picture, and I think that's what they were doing here, it's not labeled, the wavelength is going to get shorter. Do you all see that? The wavelength here, let me get a color that you can see. The wavelength here is shorter than the original wavelength. You all see that? I can go like, there we go, shorter, right? So this is what we call blue shift. This is blue shifting. Blue has a shorter wavelength, so this is the blue shift. When things are moving towards us, we call it a blue shift. You may have already guessed what the second one is. When I look at the side that's moving away, I can see that the wavelength became longer than the original, right? When I have a frequency, when I have a decrease in frequency, I'm going to have an increase in wavelength, and this is what we call a redshift. Okay. And you know how to calculate that. I put these two pictures together. Oh, let's look at first, I want to look at first the emission spectrum of hydrogen. You all see this is, I don't expect you to know that just looking at it. When you look at emission spectrum enough, you would recognize this as the emission spectrum for hydrogen in the visible range. There's a lot of wavelengths being emitted, but this is for humans, the visible range. And you can see that redshifted, the middle is no motion, right? No V relative here. That's what it normally looks like. This is normal. Okay. For redshifted, remember when it's moving away, we can see that all of these wavelengths have been shifted in the redward direction. As opposed to when we were moving towards, notice that the wavelengths are moved in the blueward direction. So that's where the expressions redshifted and blue shifted come from. Okay, what we're going to do is I picked out a problem to look at that has to do with this one line here. This is the H alpha line. Okay, the H alpha line. It's a particular wavelength for hydrogen, and when we're looking at stars out in space, stars contain hydrogen. We can look at this line and measure what that red line is, that red emission line coming from stars are, and determine whether that star is moving towards us or away from us and at what speed. Because if we measure that wavelength, we can compare it to what we already know about the emitted wavelength. Okay, so H alpha line shift. This is the example problem. H alpha line is a red visible spectral line in hydrogen atom with a wavelength of, there it is. Very particular. Notice that there's 4 sig figs in here. Consider 5 distant stars labeled A, B, C, D, and E. The light from these stars detected on Earth, and after performing spectral analysis, the following wavelengths were measured, and they give us the wavelengths. The questions down here ask about the speeds of the stars. Are they moving towards or away? And which one is fast and which one is slow? I think we can do a coarse grain analysis on just the wavelengths and ask ourselves, do we think it's moving towards or away from us based on just if it's larger or smaller than the original wave, right? Because that's what the shift says. If we have a larger wavelength than the original, right? If we have a larger wavelength than the original, we're going to have it moving away. If we have a smaller wavelength than the original, we're going to have it moving towards. So I went through and highlighted these. You can see that I highlighted them, and I also highlighted them in specifically different colors. The darker pink here are the ones that have been shifted higher. So we know that these are away. This is away, this is away, this is away. And the blue ones are blue because they are shifted smaller. Notice they're shifted smaller. And so that means that they are moving towards the star. All right. So now that we have those identified, if lambda observed is less than or greater than lambda of the source, it's moving away. Okay, so I have those highlighted. And we can get our equation out here and decide like, if we have moving away, then I want a larger wavelength, and then I'm going to put the positive sign in the numerator and the negative sign in the denominator. If it's the opposite, I can switch. If they're moving towards each other, I put a negative in the top and a positive down in the bottom. So what we need to do, you can already answer. It moves, select answer. You can already answer this. Is it moving towards or away, right? You can answer those. But it actually wants us to calculate values for those speeds. So we're going to have to use this equation, and another thing in here is we're going to get in a little bit of an algebra mess because we're solving for that V value in that equation, which is not trivial. Please, when you're doing this, I want you to show all your work, of course, for me, in anything that you turn in for me, and keep track of your algebra very clearly. Don't lose your signs, don't lose your squares, or square roots, all of that. So I'm going to do some algebra on this problem. I'm noted up here on this slide which ones are toward, which ones are away. And so I'm going to do some algebra on this equation and solve for V. I think the first step is you want to divide by lambda S on both sides, that source wavelength on both sides, and then square both sides to get rid of the square root. And that brings me to this step here. All right, I divided by lambda S on both sides, squared on both sides, I got rid of the square root. I'm going to have to do some finagling in order to isolate that V term. I think what I do is I multiply by that denominator on both sides. You see I multiply by the denominator on both sides. I took that and put it over there. That's this step here. I'll probably distribute and move things around. You see I distributed that theta, that lambda term to both of these terms in here, and then now I'm going to gather up my V terms together. And they'll look like that, and I'm solving for V. You can see that V value right in here. I'll end up having a ratio of those lambda terms and then multiply by C. I'll get a fraction of C. Sometimes stars move fast, sometimes stars move slow. You never know. Usually they're slow. They're kind of slow compared to light, of course. Anyway, so when you solve that, you get this equation. C times this stuff, this fraction of things. Okay, it's a little messy here, but you can see what's going on. I decided that I'm going to have to solve in order to figure out the speed of the slowest star and the speed of the fastest star. I'm going to have to calculate all the speeds. So I went through and I used that equation and switching the plus and minus as I need to in order to take into account moving away or moving towards. And I solved it in meters per second. I guess I could have left it in fractions, but these boxes definitely want the values, so I went ahead and just calculated the values in meters per second, and I got these values. You can go through, and of course if you have your own problem, you were probably given different numbers, you'd have to solve for your own values, and I just solved for all those values, and then I went through and I evaluated them, right? So A, D, and E are all moving away, so I just picked the speed of the slowest star. Oh yeah, you can look at these and then match up whether it's moving towards or away, right? So it looks like the slowest star is D and the fastest star was A for me. I don't know what yours are. And I was just looking at those magnitudes of those values. And so now I can enter all of the information I need to answer this problem. What you really need to pay attention to on this problem, just to highlight, is what did you need to pay attention to? Towards or away, right? Do I expect that observed wavelength to be redshifted or blueshifted? And then that will help me be able to help you be able to set up these signs up here, whether you want a plus minus or a minus plus, depending on redshift or blueshift. The last thing is all of this algebra here, all of that algebra. Make sure you are doing your being very detailed and paying attention to all your steps when you're doing that algebra. It's not a hard concept overall, Doppler effect and shift, but it's the details of the problem solving that I see that students get stuck here on. So again, good luck and have fun.